Hello everyone, I'm going to continue with 4.4 and you see I've changed the title slightly. I'm calling it Fermat's little theorem in discrete logarithms. There are two topics that we still have to discuss in 4.4. So the first one, let's start with Fermat's little theorem. So Fermat is a French mathematician. Well, in fact he was actually a lawyer, but he was an amateur mathematician, and you might have heard his name about Fermat's theorem, which is different from this one, and that's why it's called the little theorem. And Fermat's theorem was a famous theorem that was for a long time an open problem, and then finally in the late the end of the previous millennium, Wiles and with aid of some other people was able to finish the proof of this theorem, which and so let me just for context, Fermat's theorem, when you hear about Fermat's theorem, meaning the big theorem, that's called Fermat's big theorem, is the statement that if you take a power, let's call this perhaps m here, no, let's leave it b, I'll leave it b, that if you take the sum of two pth powers, that can never be a pth power. Unless, of course, p is 2, because we know for p not 2, but any other prime number, and in fact any other number bigger than 2, this can never happen, where a and b of c are integers, non-zero integers. So let's say a, b, and c are non-zero integers. So this is always true. So sum of two cubes is never a cube. That's most likely that's how you hear it often formulated in the term of in the case of the cube, but it's also true for the fourth powers, fifth powers, sixth powers, any power, except for the square, of course, because remember 3 square plus 4 square is 5 square. This is so-called Pythagorean Theorem, and very often when you do study trigonometry, you see these special trigonometric. You see very often right angles with these sides 3, 4, and 5 because they very nicely add up, right? Pythagorean theorem, but it doesn't exist for higher p. It is impossible. And that was Fermat's theorem. Now it is somehow wrong. It was for a long time not really a theorem. It was something he said it was true, and then a bit later he kind of recanted the fact that he proved it, and he gave proof for special cases, in particular the cube. And so a lot of people were trying to prove this in general, and there was a lot of success, and there were also a lot of mistakes, and a lot of fake proofs, and a lot of wrong proofs, and it took really a long time before they solved it. And per se, as a question, it's not such an interesting question, but all the mathematics that came out of it was enormous and has really galvanized mathematics, just trying to solve this little problem of Fermat. And it's now proved, so it's now called a theorem. So theorem, well, in mathematics, this is a very formal word, right? Theorem. You can only claim something to be a theorem if it's important and it has been proven. Okay, now Fermat's little theorem is a theorem, again, and actually Fermat himself proved it. And so that's the one that we're going to talk about, not this one. If you want to read about this one, Google this. It's a very fascinating story, just the way it was discovered and proven finally. But trust me, the proof is not something you can read. When I was a young graduate student, it happened during the time that I was a young graduate student that it was solved, and I went to a one-week conference explaining the proof, and believe me, I understood perhaps 1/10 of the whole thing. Now I understand a little bit more, but I still haven't really been able to grasp the whole proof. It's extremely long, and a lot of mathematics is involved. But not luckily the Fermat's little theorem. That's the one that we're going to focus on. So here it is very important that P is a prime, and I will talk about this a bit more, but let's formulate it first. So P is a prime, 2, 3, 5, 7, whatever prime you like, and then we have that if you take the P minus 1 power of any number, it's always 1 mod P. Well, I shouldn't say any number. If P does not divide A. Because if P divides A, what do you have then? So this means if A is not equivalent to 0 mod P, right? dividing a is exactly saying that you're equivalent to 0 mod p. It's exactly saying that the remainder by division of p is 0. So, of course, 0 to the power whatever is always 0, so can never be 1. But that's the only exception. Any other number, when you put it to the power p minus 1, you get 1. Okay, let's test this out. Okay, so what about p is 5 and a is 2? Okay, the only thing is that, as I said, 5 should not divide 2, but that is not the case. So, what is 2 to the power 4? Well, that is 16, and that is equivalent to 1 mod 5. Sure, okay. So let's take a bit bigger power. P is 11, and A is, let's say, 3. Now, this gets a little bit more tricky to find, right? Because now we 3 to the power 11, which is 10. 11 minus 1, right? So be careful. This is something you have to pay very much attention to. It's not the p itself, the exponent. It's p minus 1. So 11, so we put 3 to the power 10. Is this equivalent to 1 mod 11? That's the question. Now, how did we solve a problem like that? How did we do modular exponentiation? So we can calculate this, right? Let's do this. So modular exponentiation, how does it work? Well, you write the exponent as a sum of powers of 2. The other way to say it is you find its binary form. You write it in binary, but we don't really need the binary digits. We need to know the powers, 8 and 2. And then you start with the 3 to the power 1, and you keep taking squares. So you square this, and it becomes 3 to the power 2, which is, of course, this is 3, this is 9, which is still below 11, so we don't have to reduce it. Then we square again, so we get 3 to the power 4, that is 81, 9 squared. What is that mod 11? So mod 11, this is the same as 77 times 11 plus 4, right? 77 plus 4. So mod 11, this is 4 mod 11. Okay. Then what we do is, again, we take a square. 3 to the power 8, so we square 4, that is 16. Right? Remember, you always take the smallest, the remainder that you find, and then you square that one. Here you just write this formally, the powers, and this is the new one. And now reduce this again, that is the same as 5 mod 11. And how far do you go? Well, as far as all the powers that you need, and that's 8 and 2. So we need this guy and we need this guy, which means that this 3 to 10 is the same as 9, this is the one that comes from 3 squared, and 5, that's the one that comes from 3 to the power 8. Why? Why do we do this? Because remember, 3 to the power 10 is 3 to the power 8 plus 2, which is 3 to the power 1 times 3 to the power 2. That is the reasoning behind our method. So this is 45. What is 45? Well, that is 4 times 11 plus remainder 1, and this tells me that exactly this is equivalent to 1 mod 11 as predicted by Fermat's little theorem. So it is true. We don't have to verify this anymore. So I verified it once, but so now this is now the switch. We're switching gears. From now on, we're gonna believe this. Well, believe it's not that we're doing here a leap of faith. It is proven, but the proof is something for a high level course. There is something in the. If you're interested, there are exercises that try to explain the proof there, but for us, it's just we accept it. But now we're gonna, as I said, we're gonna shift gears because we're gonna use this to calculate very high powers to this modular exponentiation. So we have this method of modular exponentiation. I'm now gonna improve it. So modular exponentiation together with Fermat's little theorem. So let me explain what I mean here. Suppose we have to calculate. I take an example from the book for now. I'll do another one later. This is what they ask. So this is a typical modular exponentiation problem. 7 to the power 222 mod 11. So method 1, that is the method that we have discussed before, the modular exponentiation thing. You write 222 as powers of 2. Okay, that is 124 that's the biggest power. So let's remember 1, 2, 4, 8, 16, 32, 64, 128. Oh, 128. Yeah, right, 128, right? So what is remaining? 96? Do I say that right? Yep, 96. Now, the next thing that goes in there is 64, right? So 122, so 128 plus 64. And what is then remaining still? 32. 96, right? 32. And that itself is also a power. So we have it. So what we would do now is, this was just, sorry, I'm going to erase this little list now because I was just to get the binary. So that what we then would do is 7, and then we would look at 7 squared, and then we would square this again, 7 fourth, 7 to the 8, etc., right? And we would calculate this as mod 11. Now, I'm not going to carry it out, you can, because I'm going to find a shortcut. Okay, so here's the shortcut. So keep this model in mind because we still will use it later, but you'll see, I'm going to drastically reduce the size of the exponent. And this is how it goes. So this is method 2. But there is a very important caveat, a very good warning. Only works when we are using a prime modulus. Let me just say when prime. P11 is a prime, so it is allowed here. Now, okay, what do we do then? So a prime P. So we take step 1, right here, step 1. We calculate P minus 1, which in this case therefore is 10. Okay. What is this number? Remember, this is the power that appears in the exponent. Now, and this is, be careful now, what I will do, you might find this a bit strange, is I'm going to take this exponent and find its remainder, or rather, do the long division by this power, by this P minus 1. So I do, and you'll see why. I do 222, and I divide it by 10, that is 22 times 10 plus 2, correct? 220 plus 2. Okay, so now, why do I do this? I'm going to write this on the side here. Let's write out. I'll do it here, 7222 mod 11. Okay, now we see that is the same as 7 times 22 times 10 plus 2. Right? I haven't done anything, so it is really equality here. So let me write it as equal, this is equal, right? And then, again, what is this? A sum, it means multiplying, right? Multiplying exponents. But there's another rule of exponentiation, namely if you have a product of two powers, that is the same as, so look at what I do here, as a power of a power. Now it's very important that I put the 10, the P minus 1 inside. You'll see why. So, okay, this is where I am. So far I have just used rules of exponentiation, but here comes the crux. What is 7 to the power 10? That is equivalent to 1 mod 11. Why is that? That is exactly Fermat's little theorem. P is 11, A is 7, so we can apply it to 7. Remember, as long as you're not divisible by that power, it's fine. So you take 7 to the power 10, and that is 1 mod 11. That's exactly what I wrote here, right? So what does that mean? Well, this means that this guy is 1. And now, mod 11. And now I take the 22nd power of 1. Well, I don't care how big a power you take, it's always going to be 1, right? So, using, I'll write it here, that 7 to the 10 is the same as 1. I can replace this by 1 to the power 22 times 7 squared. Now this, of course, is modulo 11. Now it's no longer really equal. So this is, therefore, 49 mod 11. 49 mod 11. Right? 7 squared is 49, right? And the rest is 1. Okay, so this is what? 49, that is 4 times 11 plus 5. And therefore, this is equivalent to 5 mod 11. See how quickly I arrived at the answer which would be much longer, right? If you remember, if I would do method 1, I would have to go up to the power 128. Keep squaring, 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 so basically 7 times I have to square, and then put it together. So it's got a lot of modular calculations, and here it's basically nothing. Okay, now, I said it is, unfortunately, this method can only work when P is a prime. Now, that is not even really true, because I'm going to give you a homework assignment where you can do it for some other numbers like that are not prime, composite numbers, but it is much more involved, and then it uses the Chinese remainder theorem. So it all comes together. And it's a very beautiful exercise. It's going to take us, it's a long video, the homework solution. You will see it. You try the homework, so don't say, if you cannot get the answer in 5 minutes, that's normal, because it's a long problem. But you'll see it when you do it. I didn't assign that many homework problems for this lecture, so you can spend your effort on that one. But it's a very important exercise where we do this with not primes. But let's now just focus on the prime case. So I'm going to do another one, which is where the prime is a little bit bigger. Let's do, I'm picking something randomly. 101 is a prime. So I'm going to take, let's say, 15 to the power 6055 mod 101. I just randomly pick this, okay? So how do we solve this using Fermat's little theorem? So using Fermat's little theorem, FLT. I don't know, let's abbreviate it that way, right? So I'll put it here, that in case I call it FLT. So step 1, let's analyze it a little bit better. So first of all, of course, we check that P is a prime number. Well, small ones, you just look in a list, or you just try. Remember, what you have to test is whether it's divisible by anything, but you only have to go up to the square root. And we did this for 101. The square root of 101 is about 10, so you only have to check whether it's divisible by 2, 3, 5, and 7. These are the only primes less than the square root. That makes it very easy to check. But there are lists out there, and for bigger primes, then we'll talk about that later. So that's the step 1. P is that. So what is P minus 1? And that is the one that we use. So now we take the exponent. So I'll color it so that you see where it comes from. This exponent, okay, so it's this exponent 6055 that I calculate mod 100. Let me write it like that. So mod 100. What is that? So I have to write this as a multiple of, so that is 60 times 100, that's 6000, plus 55. So this is equivalent to 55 mod 100. So step 2, this means that I can replace this big exponent by this very small exponent, 15 to the power 55 mod 100. So this is the, sorry, I should say, this is the same. They are the same here. And I go quickly explain one more time why is that? Because 15 to the power 65 is the same as 15 to the power 100 to the power 60 times 15 to the power 55. Okay, why is that? That's just rules of exponentiation. But the whole thing is now that by Fermat's little theorem, 15 to the power 100 is equivalent to 1 mod 101. Because 101 is a prime, and if you take a power that is 1 less than that prime, then you get 1. So this whole thing is 1, and that's why we only have this guy left. So now we have to do this one, 16 to the power 55. There's a 5 here, in case this is not, let me, 15 to the power 5. Okay, now, so now what? Now we use modular exponentiation. So don't throw out that first method. Say, oh, I don't want that first method. It was a stupid method. No. We need it. Because what we have to do now is, so this is now method 1, right? So what we do is we reduce the size of the exponent drastically, right? And then we still have to use method 1. So first thing is we had to write this as sum of powers. So that's 32 plus the power, the biggest power of 2 that is goes in there, plus 23. That's a 16, so that is 32 plus 16 plus 5, that is 4 plus, no, that's what I'm saying is wrong. It's this one, right? 32 plus 16, 20, 52, 54, 55. Okay. Then we go, this is 55 to the power 1, 15, sorry, 15, 15, 15. The base is 15, not 55. Don't confuse base with exponent. So this is 15, and this is 15 square. This will be 15 to the 4th, 15 to the power 8, 15 to the power 16, and finally 15 to the power 32. Okay, that is of course just 15, and this is of course always modulo 101. But this is, we will always work modulo 101 here, okay? So this 15 squared, that is 225. Modulo 101, that is twice 101, 202. So this is 202, so what we're missing is 23. So this is 23 modulo 101. Okay, so we square 23. I'm going to go to my calculator now. I don't want to make mistakes. 23 squared, that is 529. So remember, right, this is 23 squared. I always use the smallest thing that I found there. That is 529. That is 5 times 101. That's 505 plus 24. So this is equivalent to 24 mod 101. Then we square this again. So 24 squared is 577. 576. That is 5 times 101 plus 71. 505, yeah, okay. So this is equivalent to 71 mod 101. Okay, then we square 71. 5,000, so this is 71 squared, which is 5,041. So divided that by 101, that is 49 times. So this is 49 times 101. So 49 times 101, that is, no, that's not, sorry, mistyped. 49 times 101 is 4949, oh yeah, of course. So what am I missing here? So this is 4949 plus 51 and 41, so 92, right? Yeah, let me double check. Yeah, I think it's correct. And then that's 92 mod 101. So you might say, Professor, would it not be better to use a negative number because it being much smaller? And you're right. So because if you now subtract 101, it will become minus 9, which is a much better number to deal with. But for sake of not complicating things, let me stick to 92. But it is a better choice. 92 squared, so this is now 92 squared. This is 8464. So what is that? So 846, oh, 846, sorry, let me, sorry. 92 squared, okay, and then divide this by 101, that is 83. So this is 83 times 101, which is 8383. That's 8383, so we subtract, what are we missing? 17, so 81. Okay, so this is 81 mod 101. I took very random numbers, and by doing random numbers, I didn't get nice numbers. I mean, they're all kind of chunky-ish, right? Okay. So, and then, now you have to put this together. As I said, because I choose random, everything is a little bit, we need all these guys. We need 32, so 32, we need 16, we need 4, 2, and 1. So this is going to be equal to 15 times 23 times 24 times 92 times 81 mod 100. 101, sorry, mod 101. And again, I'll do groups. So 15 times 23, that is, this 2 is 345. That is 3 times 101 plus 42. Okay, so this becomes 42. Let's do these two together. 24 times 91, that is 2084. So this is 2084. 184. If I divide that by 101, that it gets 21. So this is 21 times 101, which is, this number is 2121. So what I'm missing is 63. Okay, so this is 63. So let's write down what we have. We have 42, 63, and the 81 I have not used yet, but that's okay. I can do this in whatever order I want. So now do 42 times 42 times 63, and that is 2646. 2646, this thing, times 81, right? So, right, sorry, let me not write it that way. Let me do the calculation underneath here. So this is 2646, that is 2626, 26 times 101 plus 20, okay? So this is 20. So this is the same as 20 times 81 mod 101. That is the same as 1620 mod 101. So 101. So this is 16. So this is, of course, that's right. It's 16 times 101 plus 4. So this is 4 mod 101. So that is my claim. And so the power that I originally had was 15 to the power 6055 mod 101. Now you might say, Professor, is this really the shortest way? Because are we then, since we had to do the method here, were we not better to just keep going? Well, how far do you have to go? This is a number 6055. It is it has about 40 binary digits, so you would have to go at least 2 to 3 times farther than where we are now. So it would have been much more calculation. And you see, the numbers are not nice numbers in this particular case, also because I was not as smart as I could be, namely by, for instance, taking here negative numbers. And that would make it, notice by the way that this immediately gives me 81, because 92, if I subtract 101, I get minus 9, right? And minus 9 squared is 81. So all this reduction I didn't need to do if I was smart here. So just to point out that this is, you can do this, but always be careful if there are negative numbers, okay? Since we're squaring, it actually doesn't matter, right? So, okay. Now, I'm pretty sure that I made a mistake. I always assume I make mistakes. That's my default thing in calculations like this. So I'm very skeptical about my results. So I could use Wolfram Alpha to check this. So do I here my Wolfram Alpha? I still have it here. What is the number I was doing? Oh, look, it was the previous question was also so. This was 15, and my exponent was way bigger. So it was 6055. Please tell me that's 4. Please tell me it's 4. 44. What did I say? 4? It's almost close, right? So I don't know. 44, and it's 4. Yeah, I'm so sorry. So please find the mistake somewhere where I made a calculation error. In a test, you have the time to go over this and look at it again and again and again and try out where did you make a mistake. Okay? I took a very bad number. That's why I get such a bad result. I'm not going to try to figure it out. That's just going to take too much time. Okay, so now I said something about primes, right? It needs to be a prime, and then the question is, how do we know that it is a prime, right? So now comes people have therefore started asking, well, if this is Fermat's little theorem, if this is the case, perhaps it is even the case that if P is not a prime, then this is not true, right? And in fact, right, if you can, let's give it the simple example here. Okay, that is a pseudo prime, so I'm going to take. I'm hoping that this is a good works. Let's take is 117 a prime? So, is 117 prime? Now, it isn't, and you can find its factorization, but I'm going to use a test, and this is the, so as a test, I use the FLT test. Does it pass the FLT test? In other words, and I'm going to do it for only the FLT test for base 2. The base here is, of course, what I mean with the base is the number in the bottom here. That's the base, right? So, is 2 to the power, what should it be here? 1 less, right? Is this equivalent to 1 mod 117, I ask. Now, the only way that I can really calculate this is using, again, our method that we just did. Write 116 as a power of 2, and do the squaring thing and put it all together. Now, this is going to take us forever, so I'm going to really cheat now, and I'm going to Wolfram alpha and see what does it say. So 2 to the power 116, and we were going to do this mod 117. So what do we get? It should be 1. It's not. So what does this tell me? This tells me what? So this is, so all right. So this is the question, right? So 216. Well, if we calculate it, if we would do it our way, we should find the same thing. If you let me do it, probably I get a different number because I'm very bad with numbers. But believe me, I'm a mathematician who is bad with numbers. How is that possible, right? But yeah. So this is what we know. This is the case. So it fails the test. Therefore, 117 cannot be prime, because if it's prime, it should satisfy the Fermat's little theorem. This is a proof by contradiction, right? So we've seen proof by contradiction, so you know exactly what that means. So this is what we call a primality test. And perhaps even if 2 to the power 116 happened to be 1, then I could check 3 to the power 116. It should also be 1. And if your number that you're using is not a prime, then it is very likely that you're going to find a counterexample. Okay? So here's an example here. Let's look at the number. So FLT test for the number 341. Again, this is not a prime number. It's easy to see what the prime factorization is, but I'm not going to bother by that. I'm just going to use the test here. So I'm going to calculate 2 to the power. If, so the FLT test for bit base 2 would say, is this equal to 1 mod 341? Right? You take the number, you subtract 1 of it. If it's a prime, then this should be true. Now, it happens to be the case that this is true. If you don't believe me, I'll do it here and Wolfram alpha. So then at least it all comes down whether you believe Wolfram alpha or not. So what was the number? 340. So 2 to the power 340 modulo 341, right? We were testing that one. And you say 1. You say, aha! Fermat's little theorem holds, so this must be a prime number. Okay, but Fermat's little theorem just doesn't say it for 2. Let's do the same test. What happens if I do it for 3? Oh, it's not the case. So let me write that up here. So it passes this test, but fails the FLT test with base 3. Because 3 to the power 340 is equivalent to, what was it, 56? Whatever it was now. 341, what was it? 56, okay, 56. So it fails it, and therefore not a prime. So it seems we have a method of testing a prime. Unfortunately, it doesn't always work. There are numbers that are not prime and pass every FLT test, meaning for every base. And these are called so-called Carmichael numbers. Numbers that pass the test, so I should perhaps say that, numbers that pass the test, like this number, so this is true, right? So let me erase the question mark, but are not prime, are called pseudo-primes. I'll write it down. It's a pseudo-prime with respect to base 2. So the base 2 is, if you use the Fermat theorem test on this number with base 2, it seems to look like it holds. However, you see it is not a pseudo-prime with base 3, because it fails that test. So now a Carmichael number is a number that satisfies every FLT test with any base, but is still not a prime number. That is disappointing. One was hoping that this number that doesn't exist, but an example of a Carmichael number is the number 561. So this means it's a pseudo-prime. It is not a prime, but it is a pseudo-prime for any base. So it means, what does it mean? That if you take a to the power 560, it's equivalent to 1 mod 561. However, 561 is 3 times 11 times 17. It's actually it has a very small factor. It has a factor 3. It's divisible by 3 even. So it's kind of right away not a prime, but it satisfies this test here for any a. So that's why we call it a pseudo-prime. And they were first discovered by Carmichael. That's a pity that these things exist. But there are slight modifications to this thing where we do a little bit better. For one thing is this idea. Look, people say, if this comes out to be 1, right? If this is 1, so what would this then be? Now, p is an odd number, except for 2. Let's not talk about p equals 2. So p minus 1 divided by 2 is an even number, so p minus 1 is even, so p minus 2 will exist. So what is this has to be? Well, its square, according to this, is 1. So we expect this to be either 1 or plus or minus 1 mod p. Right? This is what this means. And perhaps it's not entirely clear, but it is true in this case. So if you take, so for instance, if you take, let's just one example of this. Sorry, let me do one example here. Let's do something with 11. So let's take 2 to the power 11 minus 1 divided by 2. So what is that? That is 2 to the power 10 divided by 2, that's 5, right? And this is mod 11. So mod 11. What is this? So mod 11, right? Okay, so that's not hard, right? We can work it out. That's, oh, sorry. That is 32, which is equivalent to 22 plus 10, so mod 11. So it's equivalent to 10 mod 11. But 10 is negative 1, right? Because I can subtract 1. So this is equivalent to negative 1 mod 11. So, okay, so I see. Now, you say it should always be minus 1. No, it could be 1. That is very much possible. But if it's not one or the other, then it cannot be a prime number. And so there are even slightly more sophisticated things that one can do here. And then there is a primality test that is nowadays in use, because it's very important, as we will see when we do cryptography, to find big prime numbers. And so one randomly generates numbers, 10-digit, 20-digit numbers, 100-digit numbers, however big they need to be, and then submit those, subject these numbers to these testing, these FLT tests, but a little bit smarter than the actual FLT test, the one that I, for instance, test like this, right? Does it pass this test? And now, it is not 100% guaranteed that if a number passes all these tests for any base, that it is a prime number, but there are theorems that say that if you test enough bases, you can control the probability that it is a prime number after it passes all these tests. So for instance, if you want to be sure that with probability, let's say 0.1%, right, That's a very, very small error. If you want to have that error, you say, I want 0.1%. Perhaps if you test 7 bases randomly, that gives you statistically enough chance that this will be correct. If it passes this test, then with a probability of 0.1%, it is a prime. This sounds a bit weird that we have these probabilities, right? And so what can happen potentially is that one has a cryptographic system in which one uses by accident not a prime, and that is dangerous because that would give wrong results. But the chances that you randomly run into such a thing is so small that we can ignore it. Now, 0.1% is not acceptable when you're dealing with state secretaries or bank secret information, and therefore one probably can reduce this to 1 in a billion chance. 1 in a billion chance. Is that the chance you want to run? Yes, because the chance that something goes wrong with a transfer between bits is much higher. So the error that you produce on your end by providing a prime for cryptography is much smaller than any other error that can occur during this transmission. Okay, so that is the status at this point of how we can test whether something is a prime. Therefore, actually, we do not know yet that testing how fast we can test primes. We don't have really yet a 100% waterproof test, but we have tests that are give such high predictive value for a prime number that for all practical purposes, that's more than enough. And for all those that many of you, I'm sure, are in engineering, so you know that exact, like in mathematics, we always want everything exact. But in physical world, in the real world, not everything has to be 100% perfect, right? As long as you're within a very small margin of error, what does it matter? Okay, so that's all I want to say about this. The second topic is discrete logarithms. It is also a very important topic. So discrete logarithms, because as you will see, some other cryptographic systems are based on this, because at the present it is still believed to be intractable, and I'll say a little bit at the end of it. Now, what is at the base of this? And that's a very important thing here. So again, P is a prime. So this is really, so this second session here is all about prime numbers, okay? And then, so there's a theorem says, it's not just one, there are primitive roots mod P. So what is this? What I mean with primitive root? What is a primitive root mod P? What this means is, so this is a number R. So we're going to work in ZP. Remember, so these are the numbers 0, 1, 2, all the way up to P minus 1, right? By the way, so notice that this is the last guy. The last guy in our set is exactly the exponent that appears in Fermat's theorem, right? So what is a primitive root? It's a number here, and it's not going to be 0 and 1. You'll see why. So it's a primitive root R. So a primitive root, I'll use capital R because you guys freak out about my little r's. So it's an R satisfying, so that if you take R square, R cube, R to the fourth, all the way R to the P minus 1, so all the powers of R are all different mod P. Let me give you an example. I'm going to do a simple example because we have to calculate a lot. So if P is 7, then I claim that R is 2 is a primitive root. So how do I verify this? Well, I take R, that is 2. That is, okay, now we have to take R square, the next one here in the list. That is what? That is 4. That is, nothing has to be reduced. This is always mod 7, right? But of course, 4 is still less than 7. Now, notice, and this is very important, because we're going to use this later as well, What do I do next? I have to calculate r cubed. So I'm not squaring this as in modular exponentiation. I'm multiplying this with another r here. So what we now generating is not by successively squaring, but successively multiplying with r. This is geometric progression. So we have r cubed here, which is 8, but 8 is the same as 1 mod 7. Oh, so what I said is not even true. Sorry, mod 7. Sorry, so r is not a primitive root. I know this now already because look, what is r to the 4th going to be? Well, r to the 4th, you could say, okay, that's 16. Okay, 16, that's equivalent to 2 mod 7. Notice, here, let's make it in red, these two powers are the same, and they're supposed to be different, right? I said all the powers up to the 6th power should all be different. So this is not, sorry, this is a little bit my mistake. Normally, if I take random, so let's take, what about r is 3? Is or not? Let's verify this. I should have put a question mark there, right? Is a primitive root. So how do you verify this? Well, we look at all the powers of 3 now. 3, so r is 3 mod 7. R square is 3 square is 9, is the same as 2 mod 7. What is r cube? That is, well, you could say it's 27, but you could also say, well, how do I go from here to there? By multiplying with r, by 3, multiplying with 3. So let's also multiply with 3 here. So this is 6. So what I'm saying is multiply with 3. That's how I do this. And this is, and here I do the same thing. This is all the same procedure. And so I keep doing this. So r to the 4th, multiply this number that you have, both sides, with 3. Okay, with r. Well, I wrote here r. Perhaps I should have written 3 here. Then it's perhaps, let me write 3 here. It might be a little bit, my thing is too bad. So, yeah, let me write 3 here. So this is 3, this is 3 squared, this is 3 cubed, and this is 3 to the 4th. So again, how do you go from there to there? Multiply with 3, so multiply here also with 3, that is 18, okay? And 18 mod 7, that is 14, plus 4, so this is 4 mod 7. Okay, so what is 3 to the 5th? Well, multiply both sides with 3, that's 12 mod 7, that's the same as 5 mod 7. Notice that we're all different numbers, 3, 2, 6, 4, 5. 3 to the 6th, that is equivalent to, do you know what this is? Yes, I know what this is. I don't have to calculate it. It's Fermat's little theorem tells me it's going to be 1, right? Well, let's verify. 3 times 5, multiply both sides with, that's 15, which is the same as 1 mod 7, because it's 14 plus 1. So here we are. So here we see, let's mark the green now, we have 1, we have 2, 3, 4, 5, 6. So they're all different. We get all the different powers as predicted. So this is a primitive root. Notice, by the way, not only get different, we get all of them. We get exactly the non-zero numbers. Of course, 0, you can never get 0, right? So kind of 0 is kind of doesn't play really here, because we're taking powers of numbers. And if you take a power of 0, it's 0, and if you take a power of something that's not 0, it's never going to be 0. Well, at least not when p is a prime. So a primitive root, it says by definition that they're all different, but a little bit more. It actually, this is ZP. A list of ZP, well, then you have to add 0, because 0 is never going to So if you add 0, and together with all the various powers of R, then you get ZP. Okay? That is what a primitive root is. And so here you see that, right? This is everything that is in ZP except for 0. So if you add 0, you get Z7, so you get Z7. Okay? Okay, so I'm going to put homework problems where you check that something is a primitive root or not. How do you check it? I showed you, right? You start calculating successive powers, and if you get repetition before you have, how many should there be? Right? You should have exactly p powers, well, p minus 1, right? Because you remember it's, we go up to p minus 1. So, okay? So p minus 1 powers. If they're all different, then it is a primitive root. If it's not, if you get a repetition, in fact, if you get a 1, if you think about it, if you get this 1, what does it mean? The next one, how do you get 1? Well, remember, this is multiplying with r. So this is multiplying with r. But of course, that is the same as r, so we get repetition. So here at this stage, I already knew, oh, this is not a primitive root. But okay, you see it here as well. Now, and this is where the discrete log come in. So, discrete log. So, I should say, again, we don't have any good way of finding primitive roots. We know they always exist. So the theorem says there are primitive roots. And as you can see, not every number is a primitive root. By far, not every number. But there are primitive roots. And again, we have no way of predicting what the primitive roots are. By the way, here is perhaps something that I should point out, because it's not a primitive root 2 here. Look at this here. Okay? Now, remember what I said here, all the way on top? We should have this, because if you square both sides, then you get this here, and that is supposed to be 1, right? Remember that this little thing that I told you here? So notice that here I do this for p is 7 and a is 2. Then I get that this is, so p is 7, a is 2. So this means this power. We're talking about this. This is this guy, right? P is 7, so this is 7 minus 1 divided by 2. This is not minus 1, but 1. So you see it can be 1. Okay? But as long as it's 1 or minus 1, it doesn't violate the Fermat's little theorem. Now, it shouldn't, because it's a prime number. Okay. So, now the discrete log. So, as I said, it's very hard for us to know, but knowing that 2 is a primitive root modulo 11. So, we now assume that it is a primitive root. That is somebody else's problem. Somebody has done the work for us and has shown that is the primitive root modulo 11. So what does this now mean? So we know, knowing that this is true, what can we say? Well, we know that every number between 1 and 10, not 0, but between 1 and 10, is the remainder of some power of 2. Okay? And in fact, there's exactly one power, right? So we saw that if you list so here, let me perhaps make this a bit more visually here, what is happening here. So let's list here the power of 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, 3 to the 6th, right? I'm writing this list, this is the same as in the same order, 3, 2, 6, 4, 5, 1. So, okay, I write it as sets. Perhaps I should, let me perhaps write it as a list, perhaps better, not as a set, but as a list. So what I'm saying is, if you look at this list, at least modulo 7, then this is the same as this list, modulo 7. And so what it says is, every number has a unique position here. So every number corresponds to a unique power, and that is what we call the discrete logarithm. Remember, what is a logarithm? A logarithm of a number is what power do you need? A logarithm is always with respect to some basis. Let's say the logarithm with base 10. So what is, so the little side perhaps, I'll do it in a different color that it has nothing to do with here. So ordinary logarithms. So what is the log 10 of 10,000? Well, how do we calculate that? You write 10,000 as a power of 10, 10 to the 5th, and that power, that becomes the logarithm. Now, of course, most numbers have not an integer logarithm, right? It's going to be, if I take the logarithm of 9,000, it's going to be 4 point something. But this is how the principle of logarithm. It's the power that you need to write your base, using your base to write, given a certain number, what power do you need of your base to get that number? So What power do you need to get 3? Well, power 1. What power do you need to get 2? Power 2. What power do you need 6? Power 3. To 4, power 4. 5, power 5. Now, you might try to find a pattern here. There is no pattern. And that is the main thing. There is no pattern. Now, this might not convince you, but you'll see it here when I do modulo 11. So, let's use now let me solve the problem and you see what I mean. Okay, so rather than making, perhaps it's a bit easier if we make our list vertical. So here I'm going to put 2, 2 square, 2 cube, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, sorry, my 2 is getting uglier and uglier, 2 to the 9th, 2 to the 10th. How far should I go? Professor, you can stop. You have exactly 10, 1 less than 11. So what I'm claiming now is, since 2 is a primitive root, every number that is going to appear here exactly once. Every number between 1 and 10 is going to be one of those. I can tell you what this one is, and I can tell you what this one is, and I can tell you what this one is, but for the rest I have to start calculating a little bit. Okay? So, knowing this, and I'll fill out the table, but I'm going to ask the question, what is the logarithm of 3 modulo 11 with the logarithm of 3. There's a couple of things I say. With base 2. Okay, let me write it. I'll write it on one thing. Otherwise, you need to see this. What is the logarithm of 5 with base 2 modulo 11. So logarithms always come with a base. That is no surprise. And sometimes in the book, I think they do actually use this notation log 2 here. But there's a more thing. This is also modulo a prime number. Remember, this has to be a prime number. Otherwise, it doesn't work. Okay. What is the logarithm of 5 with base 2 modulo 11? How do you find that? And you might find this tedious and say, really? This is what I have to do? And the answer is, I did 3, right? I said 3. I'll do 5 as well, but let's do 3 first. It is a tedious calculation, and that's good news because it makes it hard to break. And that's the reason that we're going to use this in cryptography. Okay, so what do you do? Well, we already started our table here, and then we stopped because we said, okay, the next number is 16. So this is 16. But that is actually equivalent to 5 mod 11. Right? This is all mod 11 here that we're working. Everything is mod 11. Okay? So this is 32. Or, if you want, perhaps better is, but do you know a better way? Yes, there's a better way, right? To keep the numbers small, I can say, okay, how do I get in the next column that is multiplying with 2? Well, let's multiply with 2. That is 10. And I don't need to reduce anything because 10 is already good. So how do I get here? This is multiplying with 2, so this is multiplying with 2. So this is equivalent to 20. Now let me get rid of these little guys here. 20, of course, needs to be reduced. That is 9, right? Mod 11. So what are we waiting for? We're waiting until we see 3. And until if we haven't seen 3, we have to keep going. And you cannot skip a single beat here. Everything has to be calculated. So the next one, we double this, multiply with 2, so this is the same as 18, which is the same as 7. No, not there. So we double again. This is the same as 14, which is the same as 3. I got it. So we see the answer is 8. It's this exponent, sorry, the exponent, not the 2, that is the answer. So once we know that 2 is a primitive root modulo 11, and if it's not a primitive root modulo 11, it might not work. But if we know this, we know there is going to be one power, and only one, exactly one power, that corresponds to that number that we want. At least now, because modulo 11, right? We always work modulo 11. And notice, in contrast with the usual logarithms that have very often decimal numbers, this is always an integer, and in fact a number in ZP. Right? A number between 1 and p minus 1. So these are really numbers. That's the beauty of this. We can use them to encode and encrypt things. And the way to find it is just to walk through the whole thing until you hit it. There's no shortcut as far as we know. And in fact, so the problem, this is called the problem of discrete log, is considered to is an NP-complete problem. Now let me remind you what, perhaps not what it means, but the implication of that is. It means that so far it is an intractable problem. It is very easy to check. Right, if I tell you that the discrete log of 3 is 8, what you need to calculate is 2 to the power 8 to verify. So I claim that the log of 5 with base 2 modulo 11 in this case is 4. So now you say, oh yeah, because I see it. You're right. But that's not the issue. The issue is that I can check this very easily. Check. How do you check this? What I have to do is I take 2, my base, raise it to this exponent, and then verify that is equal to 5. This is what I have to check. Is 2 to the power 4 equivalent to 5 mod 11? Now, these are extremely small numbers, but remember, that doesn't matter how big this number is. We have a very fast method of calculating this number, so we have a very fast method of comparing this. The fastness of this modular exponentiation, if you remember this, was log n. In fact, it is now even better because we can use Fermat's theorem, which reduces these big exponents. So it's no longer in the log of n, it is just going to be a number smaller or equal to the exponent. Oh, there we go. I don't know what happened, people. I hope. Oh no, here's my thing. So it is very easy to check. Remember, that's part of the NP. Non-deterministic polynomial means, or you can check your answer in polynomial time, but to find it, you have no other choice than to go walk through these all gruesome calculations until you hit it. Now, of course, these are small powers, but imagine you're dealing with a number of 100 digits. This means you're going to have, and your discrete log is perhaps halfway. That still means checking half of the numbers of a 100-digit number. That is still a lot, right? It's still 100. That's in general still a 100-digit number. So it's an enormous calculation that you have to do to find it. But once you find it, it's very easy to check. Keep that in mind, because that's going to be the crux, the reason that we can use these things in our cryptography. And that's what we're very soon going to start talking about. Okay, so I'm going to leave. I did a problem of everything, and there's going to be homework problems where you can check it out yourself, try yourself a little bit more. The numbers I'm going to keep a bit small here, and then there also will be a test on it. And I think then we're going to have one more session on applications, and then our main application will be cryptography. All right.